Okay, yes, sir. Can we start? Yeah. Okay, so I think we have to start off with the fourth chapter, right, sir? Turning effect, force, density, and pressure. Okay. So a quick intro about this chapter. First, the major differences. All the other chapters they go uh, like more advanced than IGCSE chapters, but this chapter will go only less advanced than whatever we have learned in IGCSE on this topic. So, except this density and pressure. That also we have seen these equations in IGCSE, but we didn't do any problems on that one. So otherwise, all the concepts in these chapters are pretty basic. So we can call it like just one step from IGCSE level. Okay, that's the idea. Yeah. So now, okay, so we have first turning effects of forces. Okay. So before going into turning effect of forces, first we want to understand what are the effects of forces. So can you tell me if there is an object and the force applied to the object, what are the effects we can receive from the okay, what are the effects we will see? Super. So one, the force can alter the motion of the object. Okay. So in motion, particularly what quantity it will vary or alter, speed, velocity. Okay. So we call it if a force is applied to an object and if the velocity of the object changes, if it increases, we call it an acceleration. If it decreases, then we call it as a deceleration. Okay. So primary effect of force on the object is motion. That motion in terms of velocity, it will change, increase or decrease. Okay. Second, what else? What else can happen apart from motion? Let's okay. Super. Compress. It can compress the object. Stretch or compress. Okay. So this is in the case of some resistance to the motion is happening. For example, let's say that there is a box in a free surface, and if I push the box, it will move because compared to what force I am giving, the resistance force is very little, so the object will change its motion or change its velocity. But if I push against the wall, it's not going to happen. The wall is not going to move. But instead, my hands will compress, the palm will compress, or if the wall is so weak, we will punch through the wall. Okay. So it can alter the shape, size. So we call it compress or elongate. Okay. So it can have effect on shape and size. So we call this as deformation. Okay, so this can be any change in the physical quantity in terms of shape and size. It cannot alter the color in directly, but if like let's say that if it's temperature dependent, yes, that is possible. Otherwise, let's say that we want to crush a paper or we want to stretch a spring, force is involved, but the velocity remains same because the force is being utilized on this matters. Okay, so it is combination of these two, the effect of forces on the material, whatever we are interested in. Okay, so for example, let's say that so here is a car moving and here is a wall, and this driver is, let's say, he's drunken and then he's running towards the wall full speed, and this is a very strong wall. Okay, so this wall will not even shatter if the car hits at full speed, let's say 100 km per hour, not full speed though, but let's say. Okay. So if the car hits the wall, let's assume that the car is made up of imaginary material, adamantium from Wolverine or something. Okay. And the wall is fully made up of granite stones and then it will not shatter. change. So what the only possible change can happen is the velocity of the car. So it will rebound with the exact velocity. Okay. So this is the case. What we call it as unstoppable force meets immovable object meets immovable object. Okay. So the idea about what happens by in terms of physics is very limited because we can't expect this will go this way, this will go this way. But if we restrict the things, let's say wall cannot be shattered and the car will not deform, then we can simply take this as a momentum problem. So total momentum before collision, we can take total momentum after collision, right, sir? But in reality, this is not at all the case. Some of the energy, some of the energy is utilized to break the, let's say, front portion of the car. Some of the energy is utilized to shatter the wall. Some of the energy will hear as a loud bang. You can hear a small spark there. That is also a form of energy. So the force is utilized in the combination of, in this case, reducing the vehicle's velocity, also deforming the velocity. In this case, momentum. Momentum is conserved, but the kinetic energy is not conserved. Inelastic collision. Yes. Okay. You got it right. Okay, sir. So this is the idea. So we always have to look for the combination. What are the ways of this force being distributed? Okay. So all the ways we have to account. And third and most important thing is the idea of resultant force. Okay. So whether it is change in shape or size deformation or it's change in velocity or motion, all these things happens only with relevant to the or respect to the resultant motion. We don't care what force we give. We don't care what force it opposes. All we care is what is the resultant force. According to that only velocity will change. Okay. So in any force involved calculation, first we should ask this question. Is this the only force or is there any other force involved? If there is any other force involved, then we look for resultant force. With resultant force, we do, even if it is F equal to ma, F divided by m for acceleration, we do only resultant force. Okay. Yes. Yes. We should always ask this question. Is there any other force involved? That's all. Sometimes the force is not given evidently. For example, gravity is always there. It can be put in electric or magnetic field. That force is always there if it turned on properly. Okay. So we have to look for if there is any other force. Okay. So these are the basics. Yeah. So now let's ask what is the turning effect of forces. So these are the linear effect of forces. If we assume that the motion has been limited to one dimension, then if you push, it will move that way. Now, now let's ask this. Let's say that I have a hinge. We'll take a hinge. Okay, here is a wall, and then I fix my rod, and this rod is anchored one side to the wall using a hinge. So this can move up and down freely. Okay. Now, if I apply force anywhere on the rod, the wall is not going to move. The only possible motion, for now, let's assume that this rod is not going to deform. Okay. So if we give force, it doesn't matter whether you choose to give here or here or here. The velocity of the rod is not going to change. What will happen? It will turn either clockwise or anti-clockwise. This is what we call it as a turning effect. So the force is utilized to turn. Remember, changing direction is different from turning. Okay. So here the force is only utilized to turn. So that's why it's called turning effect. So where turning effect comes to account, if one place of the object is anchored permanently, that point does not move. Anchored. Yes. Yes. So it can only possible motion is rotational motion. So this is where this picture of turning effects of forces comes. Okay. Yes. Now, now let's take this same diagram. Now let's say that here is a wall and we have anchored a rod here. Will it suspend there? What weight will? No, but we didn't fix in both ends. We fixed only in one end. So what possible motion? So my question is, we are not applying any force now. Okay. Let's say in real life, there is a wall and we have hinged a rod. What will be its natural position? It will be downward. Okay. It will down like this because of gravity. So the gravity acts, gravity exerts force on this. Okay. Now the question is where gravity acts. This is entire rod is made up of mass, right? So that's why the concept of center of gravity. Okay. Now there are many definitions for center of gravity. We are going to give the simplest one. So remember studying moment of force in IGCSE, sir? Yes. Now, if you take any object, any shape for that matter, any object, where clockwise moment of force is equal to anti-clockwise of movement, only due to gravity. That's all. If you take for now, yes. Now, if you take the object and let it fall on free fall, it's going to fall right away, right? Now, if you have to stop only in one place, you have to exactly anchor here. Okay. Yes. So why here? Because only in this place, moment of force due to gravity, both sides are equal. That's the place what we call it as a center of gravity. So where you have to pivot against gravity so that the rod stays same or any material or any object stays same. That point we call it center of gravity. The definition is weight of an object may taken as acting on a single point. Because what force we are trying to counter here? Weight. So if you want to count the entire object, we should apply force entire on the entire surface of the object. This is what we would expect, right? But we do not need to. We just find the center of gravity, give the counter force in the center of gravity, and the entire object will stay same. Okay. So the definition. Yes. 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 Of course, this pivot exert upward. This pivot exerting force upward is equal to the gravity due to this side and gravity due to this side on the mass and the. No, no, no. We definitely we include. Okay, so we are going to discuss what is equilibrium. In that case, you will understand why we will definitely include. Sir, we include weight of the object. We are not. We are including weight of the object, right? In all cases. Yeah, that is nothing but center of gravity, force there. Yes. Okay. Yes, sir. Nice question though. Yeah. So now, what is the definition for center of gravity? Is the weight of an object may be taken as acting at a single point. Okay, a single point. So we use the word seems because the weight of the object act on entire body. But if you just balance that point, the entire thing is balanced. Okay, so this is the idea. Yes. Okay. So now we'll shuffle things and how to balance these things. How to balance rotational motion. This is the question. Okay. So for this question, first we need to understand what is moment of force that we learn from IGCSE. Okay. So moment of force is moment of force. It doesn't have any letter. We can give this eta. Okay. So it doesn't have any symbolic representation in IGCSE and ASA level, but we can give this letter. Now, so this is force into perpendicular distance. You remember this equation, sir? Hmm. So force into perpendicular distance. So this is a perpendicular distance. This is very important. So definition of momentum force is force multiplied by perpendicular distance. Okay. So in rotational motion, the moment we call it as a rotational motion, some point is fixed. That point is not going to move. So the motion is confined to only either clockwise or anti-clockwise. So the effect due to this moment of force will be either clockwise or anti-clockwise. Okay. So if you want an object not to move due to moment of force or due to any force applied on a fixed object, then you should take care of this clockwise. All the clockwise moment of force is equal to all the anti-clockwise of momentum. That's all. Clockwise moment of force. Yes. Hmm. Okay. So if you take care of this, everything else is taken care of. Okay. For this also, we have to separate the forces. What are the forces acting? Many times they will not give gravity evidently, but we have to find. We assume, okay. Now, so that will come back. Is it clear, sir? Yes. Okay. So now, so before leaving this topic for problems, we just want to understand only one thing. Okay. So whatever we are dealing in rotational motion is called rigid bodies. Hmm. So what do you mean by rigid? Something strong. Okay. Something strong, the shape will not change. By physics definition is distance between atoms or molecules will not change. They are constant. Okay. Why? Yeah, but they vibrate about fixed point, right? That point does not change. Okay. So why we want to take this is instead of steel rod, if you take rubber rod, can we talk about moment of force? That's why. So all this rotational motion only work for rigid body. Okay. So rigid body meaning the object shape, size, and distance between molecules are fixed. Uh, the, whatever the object we want to discuss for rotational motion here in ASL level. Okay, so we only talk about rigid bodies. Otherwise, the idea will not work, right? If this is a rubber, it doesn't matter whether you pivot it or hinge it, it's going to slag right away. Okay. So one more benefit of taking this consideration as a rigid body, center of gravity of rigid bodies are fixed. They don't move. It's a point fixed. Okay. So center of gravity of rigid body is in a fixed point. Yes. Okay. This depends on only one thing, that is mass distribution. Okay. Meaning that how the mass is distributed across the ruler or how is mass distributed across the steel bar, whatever we are taking. Okay. Are we going to change the mass composition after we take into account for the experiment? So the center of gravity remains same. If you have an object equally distributed mass, okay, the center of gravity stays exactly in the center. Yes, yes. So center of gravity is in center of the object for even distribution of mass. Okay. So why we have to talk this much is, so we want to study rotational motion. So we want to avoid all the confusing possibilities. We want to take simplest cases. So that's why, is it clear, sir? Can we make, okay? Yeah, can we proceed? Yes. Super. Okay, is it clear, sir? Yes. Okay, so now second part of turning effect of forces. Now we'll take one rigid rod. Okay. Now the rod is filled with same material. So where approximately center of gravity might work, might will be in the center. So center of gravity will in the center. Toward which direction it will work? Down. So center of gravity is this. So weight of the object acts on this place. Okay. So let's say that we nailed this place in the wall. Now the center of gravity is balanced. Okay. Now the rod is freely suspending in. So if you push, it will rotate, but it will not fall because center of gravity we took into account. Okay. Now, so we will discuss different cases. Okay. So now the same rod, center of gravity fixed. If I apply force here, what will happen? So this is force, so it will move in clockwise direction. This direction calling is very important. So it will move clockwise. Okay. So now let's take the same rod, and if I apply here, so the motion is in anti-clockwise. Hmm. Yeah. But you can give it in from anywhere. Yes. Okay. Now, case C. So initially I gave force here, right? I'm not changing the magnitude of the force at all. What if I give force here? No. So same rod. In the last case, I gave force here. Now I change the force here. What will happen? Uh, so I didn't change the magnitude of the force. I just changed the position of the force with respect to the pivot. So it's going to alter the motion. Okay. So what we care is whether it's left side of the pivot or right side of the pivot you are acting. Okay, sir. This understanding is basic. I think we have we know this understanding from IGCSE. Okay. So now a little bit interesting case. So what if I give force like this? Yes, they are equal magnitude. No rotation motion. Okay, no rotation motion. Super. So, sir, we still didn't define what is equilibrium. Okay, so that we are going to do it only after. Super. Okay, now this is good. Now, case C is very interesting. More interesting of this all cases. Okay, sorry. Supposed to be exactly center, but we'll call it a bit. Okay, applying here, and I'm applying here. Now, what will happen? Uh, so if there is a same, so remember this is the same case as A, but what will be the difference? So because we are applying the twice the force, and these forces are equal and opposite. So these two forces, what we call it as a couple, force couple. Yes. So we call them as force couple. Okay. So they should be given equal magnitude. Okay. And can you see that they work in opposite directions? Opposite directions. Okay. This opposite direction with respect to pivot. Okay. What is one more thing? What makes this perfect? Equal distance. Awesome. Okay, if all these things are satisfied, the effect it will have on the rod right now, that we call it as a torque. Okay. Mm, torque. Okay. So what is torque? The turning effect due to a force couple. Okay. Yeah. So we call them, sometimes we call it as a torque couple because it's couple of force involved. That's all. Okay. So this happens in everyday life. How we open a jar or how we open a cap, anything, it involves torque. Okay. Now, so for this particular case, okay, let's let's take the length of the rod is d. Okay. Here is magnitude of F is applied. Here is magnitude of F is applied. So we want to find the total moment of force. Okay. So what is the total moment of force? This will be, now if this is the total distance is d, what is this distance? So d by 2. What is this distance? D by 2. So should we add these forces or should we subtract these forces? Because they are working in opposite direction. Both of them are clockwise. There is no anti-clockwise force. Okay. So we should add force into distance, which is d by 2, plus force into distance, which is d by 2. So in total, it is 2 force into distance divided by 2. So 2 and 2 cancel, you get force into distance. So torque is just magnitude of force multiplied by diameter or distance of the edges. Yes, same. Only if you have two forces acting, then we call it as a torque. If only one force acting, we call it as a moment of force. Okay. So if I take a circular object of radius r, and if I apply a force F, then the torque is diameter into force. Okay. Is it clear, sir? So that's about torque. So two forces are involved. The distance between the forces multiplied by one of the force, magnitude of one of the force. Yeah, we can define its effect of equal and opposite forces on rotational motion. That's a torque. That's all. Okay. So this is the plain idea. So we can complicate things slightly. We can take the rod. It's in equilibrium. So I am applying force here 30 degree. I'm applying another force here 30 degree. So how to find torque? Remember, it's force into perpendicular distance. So we have, let's say that this is force and this is force. We have to find the perpendicular component of the force. That's all. Yes. So this will be 60 degree. 60 degree. So you will get, if how do you find vertical component of this force? Yes. So F sine theta. Here it is F sine theta. So here torque is, if the distance is d, then F d sine theta. Remember, if the angle is given inward, if it's given directly outward, then you call it a cos theta. Yes. No, if this angle is given 60 degree, so we are working for 30 degree, then it is cos sine theta. Remember, only this angle was given. If this angle is given, opposite is vertical force, right? So this is F cos theta. Sorry, F sine theta. If this angle is given, then we have to work this, so that will be F cos theta, depend on which angle is given. Okay, maybe I'll draw a clear picture so that you understand. Okay, if this is theta and this is F, We are interested in this. Which one is f cos f sine theta? So if this is theta f, and this will be f sine theta. Okay, sir. So if force is given with some angle also, we can find the vertical component of the force perpendicular to the center. We can use that. Is it clear, sir? Yes. So now it's time to discuss equilibrium. Okay. So now equilibrium, only two conditions. So first we know that from IGCSE, no resultant force. That's all. No resultant moment of force. Okay. So no rotational motion is happening, no linear motion is happening. Then only we call an object is in equilibrium. Okay. So now whenever they say an object is in equilibrium, then it means we understand whatever the rotation motion forces are involved, they all are balanced. Meaning all the clockwise movements are balanced with all the anti-clockwise movements. Okay. So we can do only one small example. I think that will be more than enough. Now let's say that here is a wall and here is a rod. It's hinged. Okay. Now here is a rope tied to this end of the rod. If there is no rope, what will happen to the rod? It will fall down. So it's no longer in equilibrium. It is rotating. But when we tie this rope with the rod, then what are the forces involved? So one here is F. Uh, sorry. So this F is weight of the rod. Now tension in the rope. Two forces are involved. Which force is balancing these two forces? Uh, so force that is happening in the hinge. So this will balance. Okay. Yes. Yes. Hmm. Yes. Okay. So here is how most people make mistake. Okay. Now let's take this case, easier and simpler case. Okay. So let's say that the rod is flat and here is a hinge and this is how it's connected. So tension T act here, W act here, right? Now this is some angle theta. So this will be T sine theta. Okay. So now if you want to draw the vector diagram for these forces, okay. So we take one point, then we try to draw vector diagram. Okay. So T is acting in this case, right? W is acting in this case. So what will be the resultant force of these two? Here. Okay. But so this is the resultant force. But if this is the case, the entire system will move in this direction. So the hinge should balance the opposite force with this direction. So this is what the force hinge will provide. So when we are asked in MCQ question to draw the complete diagram, it should be how you connect these three: tension, force provided by the hinge, and weight, not using the resultant force. Okay, because clearly we are labeling it. This system is in equilibrium. So we should involve one, two, three forces, not this resultant force. That's where most of the resultant force MCQs go wrong. Okay, have you made this mistake before, sir? Super. Okay. Now this is the idea. So now how do we form vector diagram? Is this so we can uh, have We should not change any direction. H here, so W here, T here. It will act like this. It's a closed triangle. Okay. Yes, sir. So that's with to equilibrium. Yes. So this is how we draw forces for equilibrium, not taking account of resultant force, but what equal and opposite force must be provided to counteract this resultant force. This force is very important. So this is the force it will act in the hinge. Mm, mm, yes. Mm. So you have to break it into two steps. First, what are the forces involved? Do not worry about the hinge. Okay. Now weight is involved, tension is involved. Draw the diagrams. Find the resultant force. Some external agency should supply this resultant force. Then only the system will be in equilibrium, right? Find the what is the equal and opposite resultant force, where to place it. Where we will place it exactly in the hinge. That's all. Okay. Is it clear, sir? So this is vector triangle to represent coplanar forces in equilibrium. This idea is very important. Equal and opposite force. Then only the system is in equilibrium. So otherwise, if we have to draw the diagram, then it will go like this. So I can draw the wrong diagram here. Okay. So I'll take T here, I'll take W here. As a result, you will have resultant force. So which is wrong diagram. This is the right diagram. Because if this is the case, the entire system is not equilibrium. They are just moving like this. So you are applying weight and tension. Okay. So let's forget about the rope and the hinge. If these two forces are acting, the system will move like this, right? Yeah. Okay. Maybe so I can explain this with simple case. Okay. Now let's take a box. One person is pulling with F1, another person is pulling with F2. So what will be the resultant force or resultant movement? So it will go like this. So this will be the resultant force. Yeah. Okay. Now let's say that there is a hard pole here and the box is here. This is a concrete pole. It will not move. Okay. Now here is same F1 and F2. Will the object move? In the second case, it is in equilibrium. What is the difference between first case and second case? So in the first case, no resultant force is not blocked. In the second case, resultant force is counter blocked by the force hinge. What is the hinge here? So here it acts as a counteract for the resultant force. So now you have to draw the diagram like this. So resultant. Okay, is it clear, sir? Does it make sense? Yes. Super. Okay. Yeah. So the last topic. That's all. Two topics are over in this chapter. So it's 4.3 density and pressure. Sure. Yes, sir. Okay. Um, yeah. So what is the definition of density? So density is mass by volume. Okay. We also know the definition of pressure, force by area. By the way, moment of force has the unit of Newton meter. Yes. So moment of force is Newton meter. What is the unit of momentum? So can you give the moment of force SI unit? Moment of force. So it is force into distance. Okay. Moment of force is so mm, kilogram meter second power minus 2 into meter. So kilogram meter square second power minus 2. So that's moment of forces SI base unit. Okay. Wow. So try doing it for momentum, mass into velocity. So kilogram meter per second. This is kilogram meter per second square. Something else also have Newton meter as unit. For energy, what is SI unit of energy? Try. Please try. SI base unit of energy. Take half mv square. Half doesn't have unit. Sir, it's half mv square. Half doesn't have unit. M is mass. So kilogram. Velocity square. Hmm, hmm. Can you see that moment of force and energy, they have same SI base unit? Yeah. Okay. So both moment of force also you can call it Newton meter. Yes. Hmm. Take mgh also. Take mgh. Right. Okay. So it doesn't matter. So this is what we discuss in homogeneity of physics. Okay. It doesn't matter what energy we are discussing about. It always end up having kilogram meter square per second square. So energy and moment of force, they have the same unit, but they are not same. Yes, please. Mm. Yes, power is energy by time. Mm. 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 Yes. 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 So you can derive it in any equation. You will get, even if you use energy is V into I into T, still you will get the same. Yeah. So power is I square R, right? But you have to work for first I SI unit of I and R. Yeah. But it's okay. It's okay. Still you will get the same unit. Yeah. Nice question though. Yes, sir. Is it okay? Yes. So we know that density is mass by volume and pressure is force by area. Okay. Now we want to understand, in order for an object to experience pressure, it should have a force. Okay. If there is no force, no pressure. Right, sir? Hmm. Now let's take two cases. So let's drop this object. Let's take a cube and drop it. It will reach the ground in certain time, right? Okay. Let's take the same cube and fill that up with the water and release it from the same height. Will it reach in the same time? No. So clearly, tub with water exerts some force upward. That's why it slows down. Okay. So that force is what we call it as upthrust. Okay. So upthrust is the force. So actually, it's a fluid. Yes, yes, yes. Okay. So upthrust is the force in fluids. Okay. So it does two things. If the force is heavier than the upthrust, it slows down the force. Okay. If the weight of the object is less than the upthrust, it slows down. If sorry, if the weight of the object is more than the upthrust, it slows down the object. If weight of the object is less than the upthrust, it makes the object float. Yes. So because of the density. Okay. So because of upthrust only, objects float if density is less. Okay. Yes. We should not confuse upthrust with drag. Drag will work in any direction. Doesn't matter how you are moving inside the liquid. You will get a drag. Upthrust act only in this. Yes. No, no. Both are contact forces. Okay. Upthrust act only vertically, upward in the liquid. Okay. So you try to push something into the liquid. So it works against it. That is upthrust. Okay. So if you move sidewards, there will be no difference in upthrust, but still you will have a drag because you are moving inside the liquid. Okay. So if you move up and down, you will see the variation in upthrust also acting. Drag is also acting. Okay. If you move up and down, you will see variation in upthrust. But if you move horizontally, you will see no variation in upthrust because upthrust depends on the height. But still you will see drag. Okay. So do you remember we discussed about conservative forces and non-conservative forces? So where the path independent of the path, we call it as conservative force. Dependent path, non-conservative force. Okay. So, so drag is it doesn't matter which direction you move inside the liquid. With whatever force, whatever velocity you are moving, I will oppose it. That's all. So drag is with respect to velocity. Upthrust is with respect to force. Okay. Especially whatever the force you are trying to go down, whichever the force you are trying to decrease or increase the height, in that direction, upthrust will have an effect. Okay. Yes. Is it clear, sir? Vertically, all sides. No, no. Drag work on every. Doesn't matter which direction you are moving. There will be drag. But upthrust, you will see variation only if you move up and down. Okay. Is it clear? Yes. Okay. A ship is here. It will experience the same thrust if it moves 5 kilometers in the sea. But if you take a submarine, if you sink it, then upthrust is greater. Okay. So upthrust with respect to vertical motion in the liquid. Okay. But drag is anywhere, everywhere it's there. Yes. Okay. So now we want to derive this. Okay. Now let's take an object. Maybe we'll take a cube. Um, okay. So better than the cube, we'll take liquid. This is very easy. Okay. So now let's take a tub. We fill it with liquid whose density is rho. Liquid. Okay. So we are going to assume this liquid has uniform density all over. Okay. Now the liquid will have mass, right? So that mass is m. Okay. So now we are filling liquid in the tub, right, sir? So this liquid will exert a pressure here in the bottom. Okay. Why it exerts pressure? It has mass. It has mass. As a consequence, it will have force. Which force? Weight. Super. So you will have weight acting, the entire weight of the liquid acting all the points here. Okay. So we know that force here is mg, which is weight of the liquid. Okay. Yeah. So now this exert weight force here. So as a result, we will get pressure here, right? So we know that pressure is force by area. Okay. Now let's say it's the tank is cuboid. So one side of the tank is L. So the other side of the tank is also L as well. So we take it's a cuboid. Okay. For convenient reason, this section alone we take it as H. Okay. So what is the total volume of the water? So total volume of the water here is H into L into L. Okay. Now we know that pressure is force by area. Here force is M into G divided by area is L into L. Okay, sir? Yes. So now we are not doing anything tricky. We know the density of the liquid inside is mass by volume. Okay. So instead of, can I rearrange this equation? Mass is density into volume. Okay. So I'm going to plug this here. Density into volume into gravity divided by L into L. Okay. Now this is the force. This is one equation. Force is rho Gp. Hmm. Okay. Now this volume, what we can split this volume as? So I'm going to split this into rho into H into L into G divided by L into L. What we can cancel out? So rho G H. This is pressure. Okay, so we have two equations. Upthrust force is rho G V. Okay, pressure liquid is rho G H. Okay, now we choose the tank of side L and side L, right? It doesn't matter what amount of liquid we fill, the area of the bottom is going to be same. What else will change? Will density of the liquid change? No, no, same liquid. We are filling the same liquid. Same container, but different volume. So that's why pressure is property of height. So pressure is rho GH. Change in pressure is change in height. Is it clear, sir? Are we making any mess? Is it clear? Yeah. Derivation is very easy, sir. Just write a rho density is mass by volume. Volume is this H into L into L. Actually, L into L, these are unnecessary. But for AS level, this understanding is important. That's all. Okay. Now, in the pressure, is there any quantity about L? So the pressure is independent of how you are acting sideways. It depends only on your height. Yes, yes. So it doesn't matter what is the shape of the container, as long as they have same height of the liquid, they will exert the same pressure on the bottom. That varies because that, yeah, because it involves both shape of the container, mass of the container, and mass of the liquid. Yeah, yeah. Okay. So how we can be sure? Because if you connect these containers through pipe, the water height will remain same, meaning that they exert the same pressure, right? Hmm. Yes. Okay. Yes, sir. So that's the idea. So we learned two formulas. Force is rho GV and pressure is rho GH. Okay. That is force by area. That's that we do not. Yeah, yeah. Okay. So now, so we learned two important things. So one is um, for pressure. Okay. So let's say that I have one object, a cuboid. So I'm keeping it inside the liquid. So now, so it's completely submerged in the liquid. Okay. So now the cuboid, I'm going to enlarge this cuboid. Remember, this cuboid is inside the liquid. Okay. So it has six sides. So one, two, three. The bottom one is four. This one is five, and that side is six. Okay. So how the pressure will vary in these sides? We know that the pressure is rho g h. So the sides one, three, five, and six will have same. They will feel same pressure. Yes, it's a cuboid. Okay. It's a cube, not a cuboid. Cuboid. Cube. No, two and four will experience different pressure because two is uh, close to the surface, four is away from the surface. Okay. So remember this hatch, right? So this hatch is not from the ground, but from the top. Okay. So the hatch is from the top. So hatch, what we call it as depth of the liquid. So should be measured from top of the liquid, not from ground. Okay. So if you submerge, pressure, the phase two will experience less pressure than phase four because phase four is far from the top, more deeper. So it will experience more force, but same area. So it will experience more pressure. Okay. Hmm. Yes. Okay. Okay. Yeah. 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 No, still four will have more pressure than two. Yes. 1 minute, sir. Hello. ஐயோ ஒரு நிமிஷம் சரியா ஆமாய்யா yes sir sorry about that. Yeah, is it clear, sir? Yeah. So now for Just for fun, we'll take a two-dimensional object and put it in the liquid. Okay. So if you take a card like this, and the entire bottom of the card will experience same pressure because it's flat. Okay. But if you take from the top to bottom, the pressure will decrease. Because this face is flat, right? They are in same height. So the pressure will be equal in the bottom. But as you move away, the height decreases. So the pressure acting on the side will decrease. Yeah. Pressure is forced by area. We are not changing the area. Is it clear, sir? Here, no pressure. Hmm. Only until the liquid pressure will be there. If you submerge more, then all the force will increase. Eventually, you will get less pressure in the top. It does not matter. Still, there will be pressure. Ah, yes, yes, yes. Okay, that's what we are going to discuss next. What happens? Ah, mm, mm, mm. That's why we will take rigid body. So why if it flips and come? Yes, yes, yes. Because of difference in density. Upthrust is also acting. So that's why if you take the balloon, blow it big, and if you take it to the bottom of the pool, it will shrink because upthrust is acting. Okay. Yes. Is it clear, sir? Hmm. So okay. So this might be little complicated to understand, but I'll explain why upthrust happens actually. Okay. Now let's say that the tub is filled with water. You submerge something. Okay. Let's say that you submerge this cube inside. Okay. This is okay. So we'll discuss in detail because this is the next topic. Okay. Now, when this object is outside, let's take a cube. This is outside. This has a volume V. Okay. When I submerge it inside the liquid, what property of the liquid I'm changing? Liquid, remember, super. Liquid has density, mass, and volume. What property of the liquid I'm changing? Volume. So whatever the volume I am pushing inside, same volume has to be displaced above. Yes. So that's what we call it as an Archimedes principle. Yes, 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 yes. What happens? What displaced? Volume is being displaced. Okay. So now let's take a tub and fill it with exact water. Okay. Now I have a object of volume V. If I submerge this, you will the water will spill, and if you measure this water, it will have exact volume V. Okay. Yes. So this is what we call it as Archimedes principle. Yes. No, we have. We don't have the story, but we have the principle. So this idea is very important. Volume is displaced. That's why we call it as a displacement. Okay. Now you should ask the question, why volume is being displaced? Hmm. Okay. Now to submerge this object, you need to give some force. Okay. Sometimes the object is heavy, so weight itself is more than enough. Okay. So here is a person. Okay. Let's say that this person is strong enough. So if you put maybe 5 kilogram stone on his head, what will happen? He will stand or he will fall? He will stand. Now if you put 5,000, he'll fall. Okay. So if you put 5 ton, not only the stone will fall, this person also squeeze out. Same thing happened with the liquid. As you push down, the water molecules has to give way for this new object. Where this water molecule will go? Sideways, upward. That's why we call this as a upthrust. Yes, thrust is force. You're pushing it against inside, so it acts against you upward. That's why we call it as upthrust. Hmm. Yes, okay. So by pushing it, by doing it so, we cannot alter the density of the liquid, we cannot alter the mass of the liquid. What we can alter is only volume of the liquid. By which volume? Which volume exactly we are pushing it inside. Okay. Now here is a clever incident. Now let's say it's the same term. Okay. So we'll have a measuring cylinder here to measure how much flow has been happened. Okay. Now you have pushed only 40% of the cube inside or 50% of the cube inside. Then what volume of liquid you will get? So half the volume of the cube you will get. So remember, it's independent of volume of the water, how much it's filling here, how much you are submerging. Okay, how much you submerge, whatever the percentage of object inside, that volume is displaced outside. Is it clear, sir? So this understanding is very important because uh, most of the problems people get complicated because they don't find the relationship between what's the volume submerged, what's the volume displaced. Yes, yes, displaced. Okay, is it clear, sir? Yes. So can we call it? We are clear about upthrust. We are clear about pressure, hydrostatic pressure. By the way, this is called the hydrostatic pressure. Ah, yes. So I think if we do some problem, then we should be good to go. Mm. Yeah, 1 minute. Yes, yes, yes. We will. Okay. Okay. So, sir, one more thing that so I forgot to discuss here. So we discussed what is upthrust, why upthrust is happening. Okay. So upthrust is in this direction, right? Why? No, but air resistance is really not upthrust. Only if density is comparable to air. If you understand, here it is higher pressure, right, sir? Here it is lower pressure. What objects will have tendency to do? from go to higher pressure to lower pressure. Yeah, all the objects. If you take air, if you heat it, the density become very less, so they go up. So somewhere else from the air must come from somewhere else to fill the pressure. Okay, so the objects flow higher pressure means for same area you are applying more force. From that place, from crowded place, people want to leak out, right? From higher populated area to lower populated area. So in the city cases, it's different. But this difference in pressure, what gives result to upthrust? In the same area, you have less force, so less pressure. The same area, you have more force, so more pressure. So naturally, the liquid will push downward harder than top, right? So it will squeeze out of your way. So that's why upthrust is happening. Yes, yes, yes. Eventually, the resultant motion is vertical. But what's the idea? This push. Yeah, they are connected. Pressure is upthrust. In if you take that particular object, upthrust by area, that's what gives you the pressure. Yeah, okay. So let's say that the bottom area of this cube is A, and if you are pushing it down, with easily if you can push, meaning less upthrust. More force you have to supply means more upthrust. Okay. Yes. Okay. So is it clear, sir? So difference in pressure gives rise to upthrust. Hmm. Yeah. So okay. So let's solve the easiest case. Now here is liquid. Okay. And here is a cuboid. Sorry, cube. Let's take. Okay. Now this cube is anchored to bottom of the tub with the wire. Okay. Now density of the liquid is rho. Uh, mass of the liquid is m. Okay. Volume of the cube is v. Yeah. Okay. So mass of the object is we'll call it maybe. Okay, we'll call it W for easy. Okay. So what will be the tension in the wire? Do you understand the question, sir? Mhm. So first we understand. First we should understand. Okay, so give it a think. Ah, partially right. One more force is involving. Yep. Okay. Why this is very important? First, why there is T, meaning that the cube is less dense than the liquid. Then only it want to go up, right? Okay. So tension in the liquid is upthrust minus weight of the object. Okay. Now upthrust is depend on density of the liquid, acceleration due to gravity, and volume of the cuboid. So volume of the cube. Why volume of the cube? That much water you are displacing, that much liquid you are displacing, minus weight of the object. Okay. So remember, volume of the liquid is irrelevant. What volume you are displacing is relevant. Volume of the liquid is irrelevant because you can do this thing in the ocean. Do we know the volume of the ocean? No. So it doesn't matter. Only the height matters. Okay. Is it clear, sir? So think about this. If this is normal water and this cube is made up of steel, will there be any tension in the wire? No, because the upthrust is comparatively very, very less than the weight of the object. So if there is tension in the wire, meaning that we are learning Upthrust is more than the weight of the object. Is it clear, sir? So this is forming resultant force inside the liquid. Okay. So the resultant force is in the direction of. Okay. So now one more task. Draw the vector diagram for these three forces. Okay. No need vector diagram. Just give first a point diagram. Force. In which direction which force is acting. Super. Also, you have to give it with magnitude of length. Okay. So yeah, whether it's small or big depend on the force, actual force. Okay. So now mainly we have two forces acting: weight and upthrust. Okay. If there is no rope, what will happen? It will it will go towards up direction with certain velocity. Okay. That's the second problem actually. Now the tension is downward. Okay. This tension is exactly equal to upthrust minus W. Okay. So upthrust is acting upward. Upthrust is greater. Weight is lesser. So T is U minus W. Okay. Yes. Now, if you cut the rope, it will go up. Initially, it will have certain acceleration upward. Eventually, it will reach terminal velocity. Yes. Why terminal velocity is reached? Because drag. Yeah. It doesn't matter whatever direction you are moving, it will resist. So even if you go upward, it will resist. Even if you fall down, it will resist. Yes. Now I think we can clearly distinguish what is upthrust and drag. Hmm? Yes. Okay. Yes, sir. Now, I think this problem is clear, sir. Yeah. Ah, yes, please. No. Mhm. Yes. What percentage of volume of cube is below that you will take into account. So you will work for rho GV, that volume percentage. Yeah, that's it. Um, okay. So I think most probably I'll have this question here. We'll work out. Okay. Yes. Now the second type of problem. Okay. So now, so here's the same cube. Okay. It displaces volume V, but no rope in this case. Uh, so weight of the object is this, and upthrust is this. What will be the acceleration of the cube? Upward. Let's assume, let's ignore the drag now. So what will be the acceleration? Yeah, yes. So we are looking for acceleration of the cube upward. Okay. So first we should find the resultant force. That resultant force is upthrust minus W. Okay. So what is the acceleration is resultant force divided by mass of the cube. Hmm. Okay. That's how you should find. Okay, sir. Is it clear? Yes. Yeah. So this is second type of problem. Okay. So now we'll work for uh, Okay, so here's a question, sir. A ball is falling at terminal speed in still air. Okay, so a ball is falling in terminal speed in still air. So by the way, this is 9702 11 ON 14. Okay, question number 11. Yes. Oh, 1 minute, sir. Yeah. Okay. So a ball is falling in terminal velocity. Three forces are acting: upthrust, viscous, drag. Okay. So viscous drag is the same force, and weight. Okay. So remember, the ball is falling in terminal velocity. Three forces are involved: upthrust, viscous drag, and weight. So what is the order of magnitude of these forces? Okay. Hmm. Viscous will be the lowest and weight will be the highest. Okay. So from lower to higher, please arrange. Hmm. Sir, if viscous, okay, what about this viscous force? Okay. Remember, we gave one more uh, indication that this ball is in terminal velocity. Okay. So this is in terminal velocity. Three forces are involved. Okay. Just draw the diagram here. We'll take it here. So weight is acting downward. Upthrust is acting upward. Viscous also will act upward. Okay. Yes. Now, if you take the viscous force, it will be equal to the resultant force of upward and drag, right? Upthrust and drag. Sorry, upthrust and weight. Okay. So eventually, see, if there is no drag, upthrust must be equal to weight, then the object is in equilibrium. Okay. So it will just fall with the constant velocity v. Okay. Now, upthrust is there. Viscous is also there. Weight is also there. Okay. Upthrust less than the weight. Hmm. Okay. So it should be in the order of upthrust, drag, and weight. Why drag is in the middle? Because, sorry, why drag is more than the upthrust? Because upthrust, sorry, weight minus upthrust only you get drag. Okay. And eventually you are falling down. You're falling down. So as you move, you will get drag. Okay. You will keep on getting drag. But upthrust is balanced by weight. Okay. But if the drag is higher, meaning that the upthrust is higher than the weight. The terminal velocity gives you the idea upthrust is equal to weight. Okay. So it is actually upthrust is weight plus drag. Sorry. Yeah. Weight is upthrust plus drag, actually. Okay. So in this upthrust, if the upthrust is higher than the drag, the object should have gone upward, right? No. Okay. Weight is upthrust plus drag. Is it clear? Okay. If upthrust is higher, drag will drag, if upthrust is higher than the drag. Okay. Meaning that they work in opposite direction. Meaning that the object is going upward, but we are falling in terminal velocity. So the drag is higher than the upthrust. Yeah. Yes, sir. Okay. So we'll try to do one more question. So actually, we should do more question in this one. So I have a calculation question, sir. 1 minute. Because these calculation questions are very important in this chapter. So usually you can find question number 11 to 14 in this chapter. 10, 11, 12, 13, 14. So approximately any one of this number. So we will get. Hmm. Okay. So a very basic question. Okay. So here is a stack of books. Okay. So each book has mass M. And the question is, what is the pressure exerted on the table by the book? Okay. So if each book has mass M and if they have area A, the pressure will be force by area. So the total force is number of books multiplied by mass of the book multiplied by gravity divided by area. Okay. So this is a general equation, but they ask different questions in this one. Sir, is it clear? Yes. There was one advanced question. Uh, okay. Mm. That is energy question. Actually, this depends on what high you are moving. It's not a pressure question. Yeah, yeah. Similar, but it depends on how you are moving. Yes. Okay. Yeah. So here is a question. Now this we all already solved. Okay. So this is question number 14 in 9702 11 MJ. I think we already solved this question, but we'll see. Yeah, yeah. Okay, question number 4. So here is a cylinder of, sorry, here is a water and the cylinder is submerged and there is a force Newton meter. You remember this question, sir? I think we solved. Yes, yes, yes. Okay. Now the cylinder's weight is 25 Newton. Okay. Now reading is showing 10 Newton. Now the water is replaced by liquid with a density greater than, so 10% greater than the density of water. Okay. So water is replaced with 10% more dense liquid. What is the new reading on the Newton meter? You remember this question, sir? Yes. Try. Do you understand the question, sir? Hmm. I'll explain one more time, sir. One more time. So here is a cylinder suspended in the water. Okay, here is a Newton meter. Now the cylinder's weight is 25 Newton. Now the Newton meter shows the reading of 10 Newton. Cylinder is fully submerged. Now, if the water is uh, dis- what is changed with some other liquid whose density is 10% more than water, what will be the Newton meters reading? Ah, super. So we have four options. Okay, 8.5 Newton, 9 Newton, 11 Newton, and 11.5 Newton. No, no, work, sir. Find the resultant force equation and work. So actually, I can share the question. The question is on the screen, sir. Yeah, we can use it. Fine. But you need to use the right formula. Yes. Super. Mm, hmm. Okay. Yeah, it works. It works that way. But problem is, okay. So, okay, how we will arrive at answer? What's the answer? 10 percentage of 10 is 1, sir. But that's not the answer. There is one problem with that. This works only if all the ingredients are directly proportional to all each other, right? You can directly take percentage. But here it is not. Your math is right, but problem is it should be the resultant force. 10 percentage of 25 minus 10. Yes, 15 Newton. What is the 10%? Yes. No, no, sir. First, you have to find the upthrust. Okay. Now, what is upthrust? It is 25 Newton weight minus what is the reading shown in the Newton meter? 10. So, upthrust is 15 Newton. Okay. We know that upthrust is rho GV. Volume hasn't changed. G hasn't changed. Only density has been replaced with 10% more. So, what is 15% of 10? 10% of 15 is 1.5 Newton. So this will be decreased in the original reading, which is 10. So 10 minus what is 1 point percentage of 10 is 1.5. So 10 minus 1.5, which is 8.5 Newton. That's your answer. Your idea is very, very good, but you should have worked with the resultant force. Yeah, no problem, sir. But how do we solve those? Upthrust is rho GV. Okay. Now, second liquid has upthrust of 10% more. So it will be 110% or 1.1 rho GV. Okay. So we know that the upthrust Okay, I installed it in the first page. So 25 Newton weight, initially reading shows 10 Newton. Okay. Now if we do it with a liquid of 1.1 rho, that's what 10% more means. Then what will be the reading? Okay. Now this reading is upthrust minus weight. Sorry, weight minus upthrust. So first case it is 25 minus upthrust, which is 10. So upthrust is 15. Okay. So we found the upthrust 15 of this liquid. So rho GV is 15 Newton. So what will be 1.1 rho GV? Okay. This is the question. So again, instead of rho GV, we can put 15, 1.1 into 15, which is 15 plus 1.5, 16.5. So the second reading will be again weight minus upthrust. So 25 minus 16.5, which is, that's all. Your math was very good. Only you should have worked for the resultant course. Yeah, good. Yes, sir. Is it clear, sir? Okay, so we'll finish with this now. You can study for tomorrow exam. We'll continue with Saturday. Sorry, Thursday and Saturday. Yes, sir, sure. But you are free Saturday evening, sir? Yeah, sure. Okay, okay. Sure, sure. Yes, 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 sir. Yes, sir. Sure. Yes, sir. Okay, take care, sir. Yes, sir. So we started at, okay. Thank you, sir. Thank you, sir. Take care. Yeah. The guy is very busy, sir. He told me before exam he will give 3 or 6 hours, like one day, so you can clarify whatever your doubts. Yes. But I said we want to take classes in advance. Okay. So I'll check with him again, sir. Yes, 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 sir. Thank you, sir. Thank you.